Hello, everyone. My name is Mazal, and today I'll be presenting our work titled Towards Targeted Obfuscation of Adversarial Unsafe Images using Reconstruction and Counterfactual Superregion Attribution Explainability, carried out at the University of Texas at San Antonio. So before we proceed with this presentation, I want to first acknowledge that some of the content discussed may touch on sensitive or potentially offensive topics. My intention here is purely educational, and it's aimed at fostering an understanding and constructive dialogue. But please feel free to step out if you find at any part of the discussion to be uncomfortable. And I'll welcome any questions or concerns during the Q&A session at the end of the presentation. So moving on to the core of our presentation today, let's first take a closer look at the problem that we're aiming to tackle. To start, there are two key problems that we need to understand: adversarial images, unsafe images, and then the combination of the two, which we refer to as adversarial unsafe images. Simply put, adversarial images are digital images that have been perturbed such that they result in incorrect interpretation by AI-based image recognition systems. Unsafe images, on the other hand, are images that could be potentially harmful when viewed. Social networks often use AI-based detectors to flag unsafe image content. However, adversaries are using increasingly sophisticated techniques to effectively fool these detectors. Small perturbations are able to fool these detectors, all the while preserving the unsafe content for viewers. Unsafe images are known to have caused harm to frequent viewers of such images, even leading to lawsuits for mental damages. Some preliminary experiments have shown that even state-of-the-art API are vulnerable to these attacks, with an average performance drop of nearly 40%. From this experiment that we conducted, we find that existing unsafe image detection systems are insufficient in detecting adversarial unsafe images. The application of image explanations to obfuscate unsafe images is relatively unexplored. To use existing explainability techniques is not straightforward for unsafe image obfuscation. For methods like GradCam, you must first predefine a certain percentage of pixels to obfuscate, and for LIME, you could use all of the positive attribution pixels to obfuscate. This technique is not suitable for unsafe regions that vary in size and may result in excessive obfuscation, which would remove important context of the image. Other explanation methods, such as integrated gradients, provide sparse pixel explanation maps, which are not able to directly cover the unsafe region. In summary, adversarial unsafe images pose an important challenge to existing defense techniques. However, even if we disregard the low detection accuracy of these images, the existing defenses can only detect if images have been perturbed, but cannot remove such perturbations from images, which can also lead to misleading explanations. These issues motivate the formulation of our system, where we focus on removing adversarial perturbation for not only robust detection of adversarial unsafe images, but also for more robust explanations of adversarial unsafe images so that they can be effectively masked. Now that we have motivated the need for research on systems that detect and mask adversarial unsafe images, it's time to present the datasets that were used in the experiments for this research. The first dataset we use is a sexually explicit image dataset derived from an existing dataset that contains sexually explicit images as well as non-sexually explicit suggestive images alongside neutral social media images. The second dataset that we use is a cyberbullying image dataset that contains content such as rude hand gestures, threatening objects or weapons, or racist or hateful symbols. The final dataset that we use is a dataset that we collected by scraping images associated with specific self-harm related tags on Tumblr. After annotation, we were left with a dataset of 2,100 self-harm images. Following our motivation, we designed an image reconstruction system to first remove adversarial perturbation as an input transformation defense, where the cleaned input is then sent through a robust classifier. Then, explainability will be used to detect the unsafe regions in the image to obfuscate them. To overview, our system, named UGuard, contains two distinct modules. One, an image reconstruction module, which we call adaptive clustering of robust semantic representations. And two, an explainability-based image obfuscation module, which we call counterfactual superregion attributions. In general, to fool classification systems, perturbations are generated such that we shift the actual test distribution to the tail of the training distribution. The standard adversarial training strategy of training against perturbed samples is a simple and effective solution against known attacks. However, it is not necessarily robust against unknown attacks, which brings us to the next component of our method. To further enhance the robustness of our system, we also perform a reconstruction of the image to remove adversarial perturbation. We accomplish this by decomposing an image into its high and low frequency components. We then use convolutional dictionary learning to learn a dictionary to construct the high frequency component of an image given its low frequency component. Now that we have reconstructed the image without perturbation, we can safely begin to use image explainability to begin to obfuscate images. However, as was shown earlier, directly applying explanation techniques toward targeted image obfuscation is not straightforward. Therefore, we develop a counterfactual explanation technique to find the regions to mask. One of the key issues of using counterfactual techniques, though, is the exponentially large search space to find a counterfactual example. Using the intuition that attribution maps point us towards important image regions, we use these to lead an informed sampling of image regions. In our method, we concurrently split an image into superpixels and generate an attribution map with respect to the classifier model. Next, we average the attribution scores within each segment. And finally, we perform a counterfactual analysis on the top K scored regions to determine the ideal obfuscation to make an image safer. To recap, in this system, first, an adversarially perturbed image is deconstructed into its high and low frequency components. Next, the high frequency components are reconstructed using a learned dictionary that correspond to the low frequency image features. Then the image is detected as safe or not safe according to a robustly trained classifier. And then, if an image is detected as unsafe, the attribution map and image segmentation is generated, where counterfactual masking will be used to obfuscate the unsafe image regions. In our evaluations, we show the effectiveness of UGuard against adversarial unsafe images, showing both robust detection and obfuscation. We also performed several other evaluations to show the effectiveness of different components of our system. In our adversarial robustness experiments, we see that UGuard is robust to attacks that it was trained against, as well as some attacks that it was not trained against. Furthermore, in our experiments on explainability-based image obfuscation, we show that more images are made safer with less obfuscation than other techniques, which preserves important contextual image information. Finally, we also conduct an in-the-wild experiment on sexually explicit and self-harm images from outside of the training data sources. In this specific evaluation, we found that over 90% of unsafe images were made safer. In future works, other unsafe image categories could be investigated. Furthermore, our approach could be extended to be used in conjunction with vision language models for image querying to assist in protecting social media image moderators. In conclusion, our work investigated adversarial unsafe image detection systems and explainability-based obfuscation of unsafe images. In this work, we found that existing methods were not suitable for detection and obfuscation of adversarial unsafe images. We then presented and validated our system, UGuard, to detect and perform targeted obfuscation of adversarial unsafe images across 3 datasets. Image investigation professionals, such as social media moderators or law enforcement, could potentially make use of this approach to obfuscate unsafe images to protect them to protect investigators from the most harmful parts of the image while preserving the important context that is needed for them to perform their jobs. Now I'd like to open up for question and answers.